Starting today, we will discuss a book published in June 2024, titled Discovered, Not Designed: Building Things in the Age of Complexity. Its author, Sean McClure, originally earned a PhD in computational chemistry, later shifted toward complexity research with a focus on data science, and also took part in entrepreneurial consulting projects. He writes a column on Medium. This book was actually written nearly a year ago. It is indeed excellent, and we missed the chance to share it at the time. McClure captures a spirit of our era. With the success of AI large models, the things humans build are moving from the simple toward the complex. Our traditional creations, like cars and televisions, can be called simple. Engineers understand the function of each part. A specific input produces a specific output. These objects, inside and out, are the result of meticulous design. But AI large models are not like that. A large model may have trillions of parameters, yet no one knows the specific role of each parameter, nor did anyone carefully arrange them. Even the builders of the model cannot explain why it works so well. So we say the car is a simple system, whereas a large language model is a complex system. But these two terms are easy to misunderstand, since in other contexts no one would call a car simple. Perhaps we can use McClure's framing. The car was designed, while the large language model was discovered. Human design ability is astonishing. Have you ever felt awe while flying on a plane? How does something so massive fly? How does its engine work? What aerodynamic principles are involved? How does it achieve such safety, and adapt to so many weather conditions? A commercial airplane has over 1 million parts, behind which are countless ingenious ideas. Think of lithography machines, think of computer chips. The precision and complexity are awe-inspiring. But if you zoom in on some details, you may feel even more awe toward nature. Take the car versus the cheetah. On a straight highway, the car certainly outruns the cheetah. But once you move into complex terrains, sand, forests, rugged mountains, the car is helpless. The cheetah, however, can accelerate rapidly, make sharp turns, and maintain balance under extreme conditions. And it uses very little energy. Aside from top speed, the cheetah surpasses the car in virtually every aspect. I recently read a report saying humans still cannot build a robot dog at the level of animals. Another example. The rocket engine is a technological miracle. Yet as a fluid propulsion system, even a squid outperforms it. A squid can flexibly control speed and maneuverability, execute short bursts of high-speed motion, sustain long-term activity, and its nervous system senses the environment with high sensitivity. More impressively, even if injured, it can self-repair. Cut off a tentacle, and it grows back. Because our designed artifacts are far less refined than animals, we have to make nature adapt to us, not the other way around. To enable fast transportation, we must build extremely flat roads. We must simplify the environment so our machines can operate. McClure divides problems into two types. Difficult problems, which traditional engineering excels at and can be solved through design, and what he calls hard problems, which humanity has only begun to seriously address with the emergence of AI. A difficult problem, though large and messy, can be solved by stacking known functions step by step. For example, building a bridge. A small river can be crossed with a simple arch. But if the river is wide, you need deeper foundations, stronger piers, and deck structures. You must consider load distribution, material strength, thermal expansion, wind, earthquakes, etc. The bridge becomes massive, with many modules and components. But you can still design and build it. You respond to more with more. But a hard problem, what this book calls a complex problem, cannot be solved by piling parts together. For instance, how do you design a cheetah? One that can survive in various environments, remain compact, yet extremely agile? You can't solve this by adding more legs or thicker skin. You must think and build in a fundamentally different way. Complex problems and difficult problems require completely different approaches. We are good at solving difficult problems by using understanding and abstraction, together forming design. Understanding means grasping the underlying logic, clearly mapping all causal relationships, knowing what output arises from what input. But individual understanding is limited. No one can fully master an entire complex bridge. That's where abstraction comes in. Abstraction means layering, packaging, modularization. Large engineering systems are built layer by layer. Each layer only needs to understand its own logic, because the lower layer has been encapsulated. Consider software engineering. At the bottom is machine code, binary instructions. No one reads these. Above that is assembly language. With assembly, you don't worry how each instruction is implemented in the CPU, just the logic. Above that are high-level languages, like C or Python. They allow you to call functions, which encapsulate assembly code. You don't care how the function is implemented, only its input and output. Above that is object-oriented programming, where data and actions become components. Teams can collaborate by building components. Above that, an e-commerce website is backed not by one program, but multiple cooperating systems. Above that, human-computer interaction, where many business users build workflows without needing to know any technical detail. The benefit of abstraction is that, with many layers and modules, as long as each person understands their own module and interfaces are clear, the system guarantees determinism. Some believe we must understand how everything works. That is impossible. Most people don't know how a toilet works, let alone a car. And you don't have to. If your car is automatic, you don't even need to know what a gear is. Even with a manual, you don't need to understand the mechanism behind it. As long as someone understands. Design is the process of establishing clear links between low-level and high-level abstractions. But design only solves difficult problems. The understanding abstraction approach fails with complex problems. For example, facial recognition. How do you make a machine identify that face A is Johan, face B is Jack? Where is the causal structure? Is it the ratio of nose width to eyebrow length? Facial recognition systems are not algorithms in the traditional sense, because there is no describable causal structure. When humans recognize faces, we don't use causal reasoning. We use intuition. You see it, you know it. No proof. In the jungle, you see a tiger, and you instantly feel fear and flee. You don't compute survival probabilities. Your nervous system reacts directly. Our emotions, instincts, and ability to handle fuzzy problems are all products of neural computation. Neural computation and designing a car or bridge are entirely different approaches. To understand how hard problems are solved, recall how large language models are trained. As we've explained before, training involves 3 stages: pre-training, supervised fine-tuning, and reinforcement learning. Their common feature: you impose requirements externally, not control them internally. You can set the number of parameters, layers, and architecture, but you do not design the value of each parameter. They are learned. You feed massive text, let it predict the next word. It uses trial and error. Guess, compare with target, update parameters. Until suddenly, outputs look reasonable. Then you say, pre-training is done. Then you fine-tune it, and perform RLHF. You don't modify internal parameters directly. You just say this answer is good, that is bad. It adjusts itself through endless trial and error until one day its outputs meet your expectations. Even surprise you. That's when training is done. Can you say you designed this system? Not really. You did not decompose it into clear modules. You don't know what any parameter does, or which parameters encode which concepts. You just suddenly discover that it works. Discovered, not designed. This fact unsettles many people. Jan LeCun criticizes large models for lacking causal structure. Anthropic's Dario Amodei wants to understand how models work internally. If we cannot understand it, we are afraid. But McClure reminds us, some systems in human society were never understood to begin with. Take the market. No one can clearly explain why a stock has its current price. There is no clear causal structure. Price emerges from countless interactions, not from design. Or cities. No city's current form was designed by a planner. Cities emerge from migrations, building, demolition, rebuilding. And nature? Why is the cheetah's body so elegant and efficient? Can you state its design principle? You can't. It has no designer. It is the product of millions of years of mutation, iteration, and selection. It was discovered. So complex problems are not unsolvable. They just cannot be solved through design. You solve them nature's way. Apply external pressure, and let the system, through mutation, iteration, and selection, discover a solution. You cannot control it internally. By the time you discover it, the system has already solved the problem. How nature solves hard problems, and how emergence works, will be discussed later. Here, I want to address a mindset. Modern ideas like centralized planning, ideological unity, top-level leadership are essentially design thinking. Such thinking did not exist in ancient China. It came from Christianity and the Industrial Revolution. We now recognize its limitations. In reality, complex economies were never designed. Look at China's reform and opening. From household responsibility, to township enterprises, to private businesses, to coastal trade, to local competition, to land finance. None of the mechanisms that drove growth were designed top-down. They were all discovered bottom-up through practice, with central authorities merely later recognizing and legitimizing them. Deng Xiaoping was not only the chief architect, but also the chief permission giver. Greatness is not planned. Prosperity is not designed. Growth is not led. Society is not a machine but an organism, capable of self-organization. History shows that Confucian hierarchy and legalist control cannot produce prosperity. For complex societies, Taoist philosophy is most suitable. I do nothing, and the people transform themselves. That's it for today's content. Thank you for watching, and I'll see you in the next video.
If you feel there is value in this, please like, subscribe to this channel, and leave your thoughts or suggestions in the comments section. Let's grow together and read more good books.